Welcome to Cybernetics.
I'm Songyun.
And I'm Rebecca. Cybernetics is a podcast series introducing the field of cybernetics and control theory.
With our guest speakers, we'll take you on a voyage to explore a broad range of applications of the fields in the real world.
Sound complicated? Well, all we need is your curiosity. Stay tuned! Today we have the pleasure of having Professor Jochen Trumpf.
Professor Jochen Trumpf is from the School of Engineering at the Australian National University. Welcome, Jochen. It's really awesome to have you here for this episode.
Thanks for having me.
We learned that you have a strong background in mathematics from undergraduate through to PhD, and that's super cool. So what was the charm?
The charm of mathematics. Well, there was quite literally a charm, but in some indirect way. So when I finished high school, I was actually planning on studying philosophy because I'd enjoyed that very much as an elective course in my last 2 years at high school. And so I set myself up, to do civil service in Freiburg, lovely town in the south of Germany, which has a famous university with a really great philosophy faculty. And so I was all set to study there. And then I started a relationship. And, the way that the German system works with places at university, it ended up meaning that if I wanted to be in the same city as my partner at the time, I had to move. And so the place that ended up being the best compromise, philosophy wasn't really an option there. And so, because the part of philosophy that had interested me the most was logic anyway, I thought, well, logic I can also do in mathematics. And so that's how I ended up enrolling in the mathematics degree and ended up loving it. So that's the short version of it.
That's very sweet.
But do you mind if I ask, what is it about philosophy that actually attracts you in your last 2 years of your high school?
I think it's the reflective practice, that it's a discipline that makes you think about yourself, about your place in the world, about, what is going on around you in sort of more expansive ways than you get, for example, in natural science disciplines. I did end up studying physics as part of my degree at the university.
Right.
And so I have an affinity for that, but I was attracted to the broader perspective that philosophy brings.
Right. Yeah, then how did you end up coming to Australia?
Yeah, so that's, as usual, relationships between people, right? So the person who hired me at the ANU was Professor John Moore, who passed away a few years ago. So he was a close friend and collaborator of my PhD advisor, Uwe Helmke, in Würzburg. And I'd actually met John on a couple of his visits to Würzburg. And so he ended up getting funding from the ANU to hire a postdoc. And so he contacted me. It was a funny episode. I was on a train with my supervisor to Berlin to go to a conference. And so, they desperately had to reach us because there was a deadline. And so I didn't have much time to think about it. I didn't have much time to think about the fact that Australia is very far away. And so I just put in an application and so that's what happened.
Oh, wow. Well, you literally moved from one end of the world to the other end of the world.
Yep.
So I guess that's like different kind of lifestyle, I suppose.
Oh, yeah, very different. So, when I came here, I had no intention of staying. But I came for a 5-year position and, I was thinking, have a little adventure, go back home.
Exactly. Oh, wow.
I'm still here.
And I guess Canberra, Australia is treating you very well then.
I can't complain.
Okay. Oh, that's nice. That's cool. As a mere engineer, it's really impressive that you were interested in hardcore mathematics, philosophy, and physics. And now you are in the control realm. So could you tell us a little bit about your insight into control?
Okay. So maybe let me start by giving an example of what control is actually all about.
Oh, okay.
Sure.
So, the example that I like to use with students or people who haven't been exposed to systems and control theory as a field is that of hot water in a shower, because, that tends to be a daily experience for most of us.
Yep.
And so the we all have our struggles with that, where the shower is never at the temperature we want it to be at. And, if we are too impatient at the moment when we're getting into it, it's too hot, then too cold, and these sorts of things. And so control is really about building systems. So that's a term we inherited and borrowed from cybernetics, that achieve a certain desired goal. So in this case, constant water temperature at the temperature that we want it at for how long as we want it. And so control is all about achieving that. And so the first step in how we go about that is that we build a model of the system that we are discussing, right? And so in our context, model typically means a mathematical model, so some form of equation that we then use to try to find a way of influencing the behavior of the system that we are looking at. So in this case, make the shower at the temperature that we want it at. And so maybe the most fundamental concept in this modeling world is what we call a signal.
Okay.
And so this is where one of the important components comes in, which is when we talk about behavior of a system, we always at the back of our minds think in terms of how that behavior is changing over time. So that is possibly one of the most important aspects of systems and control theory in particular. And so a signal for us is a physical, or it can be chemical, biological, it can be social quantity that we can measure and that we can repeatedly measure. Right? So we get values for that quantity, say the temperature of the water hitting my skin, right? Or the pressure in the pipe that connects the pump to the shower head. So that's what we mean when we say quantity. They change over time. And so how they change over time, that's what we call a signal. And so then the modeling that we do is trying to mathematically describe the interaction between multiple signals. So how does a change in pressure affect the temperature? How does me changing the electrical input into the water heating element, so, putting higher current through, how does that change the water temperature? How does that then in turn change the pressure and so on over time?
Right.
And so this is where, another idea of cybernetics is informing our field. That's the idea of feedback. So where you think in terms of one signal influencing another signal, and that other signal in turn influencing the first signal back, right? And so how do you analyze this sort of situation? And that situation is pervasive, right? And so, from my perspective, formulating and clarifying the concepts of systems and feedback are actually probably the most two important contributions that cybernetics has made to all of science, and they are so central to our field, systems and control theory, that most people who study these days don't even know that these are borrowed terms. So they believe that we invented them. We didn't. We borrowed them.
Humble mindset.
Yes.
Yeah, that's really cool. So you talked about systems and feedback when it comes to building a control system, control model, right? Then would it be only about the system itself, or whether there would be other factors that are affecting the dynamics of the system?
Yes, so you've used the word dynamics, so we should probably come back to that at a later point.
Yes, okay.
But one of the fundamental ways that our modeling paradigms work is that they're trying to compartmentalize the world, right? So, I know that this is always a controversial way of going about things, in particular when you talk to social scientists, because they tend to use different kinds of models and different kinds of approaches. But when you're an engineer, this way of modeling and thinking where you are encapsulating parts of the reality that you're trying to model into a black box, and where you're kind of randomly drawing the boundary of that black box. And then, you're restricting your modeling of the system to the inside of that black box, and you're conceptualizing the way that the interaction to the wider world happens as specified interfaces between that black box and either other black boxes or, a black box that is the universe, the rest of the universe. Right? So that's how we think in terms of our modeling. And I guess, if you want to be critical about it, it's mostly driven by the fact that that's the only way how we know to solve problems. Right? So that's really what drives this more than anything.
I see. Practicality then.
Yes. So, this is probably where if you broaden your perspective a little bit and think about the differences in approach of different sciences, right? So then maybe that makes it more understandable. So I like this caricature, right? So where a scientist is after absolute truth, and an engineer is after approximate truth. Right? So that's good enough to achieve the one outcome that they really care about. So in this case, constant water temperature of my shower. Right?
Exactly.
Yeah. So we engineers are problem solvers.
I think that's a fair characterization. Right? And so as a mathematician, you find yourself in that curious in between position where all of mathematics deals in relative truth. So all the statements that mathematics ever produces are of the kind, well, if you believe this thing, then you also need to believe that thing. Or if you believe that this thing is wrong, then you also need to believe that this thing over here is wrong.
Yes.
So, that's the only kind of statement that mathematics can actually make. And, I know that this is not what you think about mathematics when you come fresh out of high school. But, that is what mathematics actually fundamentally is. It's about relative truth.
Yeah.
And so it marries very well with this engineering mindset of getting close enough to the truth in order to achieve the design goal that you have for your system. Because, it allows you to reason in an environment where you are not actually talking about the absolute truth, but that doesn't matter for what you're trying to do.
That's right.
Yeah, that makes sense. That makes a lot of sense. As an engineer myself, in research, we really focus on a very specific problem, and we know that there are other cases, but we don't really care about those first. Like, we just focus on that particular one. So I guess that's the approximate truth, I suppose.
Well, as for me, it's really interesting to see the different mindset between people with different disciplinary backgrounds and training. Because as for me, with my background in mathematics, I felt like, well, there are always a lot of different ways that we can achieve a goal. And when it comes to choosing the best way, it will be about like optimizing the way, right?
Yes.
Lowering or minimizing the cost so that we can make something happen without putting too much effort, right? So yeah, it's really interesting. When it comes to modeling, especially, if there are lots of ways, then how do we optimize things? And how engineers approach getting that approach right. So how would you explore such different ways then?
So there's a discipline in engineering which has existed since about the 1950s, and that's called systems engineering. So that's the engineering discipline that actually studies this question that you just put. Okay? And so, it's an interesting historical story because it was invented in 3 different places almost simultaneously. And it actually took people almost a decade to figure out that they were talking about the same things. This is usually the case.
Language barriers.
Exactly. So, it was invented for the US-American space program. It was separately invented in the shipbuilding industry in Japan. And separately invented again in Switzerland with large-scale machinery for power plants.
Right.
And so, what's common between those 3 applications is that they are possibly the 3 first kind of human technology applications where the scale and the complexity exceeded the capacity of a single person. Fundamentally. Right? So where it is just no longer possible for one lead engineer to understand the entire thing that they are trying to build. And so what needed to be created is a set of methods and tools that allow to systematically answer questions like, so if I'm looking at this part of the system, how do I now choose what model I use, right? How do I choose what I'm optimizing for without then jeopardizing what happens once that module that I'm building is put into the spaceship and sent to the moon? Right? And so being very clear about modeling paradigms, being clear about interfaces between subsystems, being clear about how you break down a system into subsystems such that you are not destroying the overall system functionality. And then how you systematically go about putting in different design, we call them design metrics, right? So different concerns, different things you care about. You mentioned cost as one driver. There are engineering methods, metrics, right? Like, you don't want your shower to weigh 5 tons, for example. and things like that, right? And so, how do you actually go about systematically exploring what we call the design space? What are all the possible compromises that you could make? And how do you then go about choosing the right, quote unquote, compromise? So that's what systems engineering is.
I see. So I think in system engineering, well, you do have, say, signals and stuff inside where you can extract whatever state that you want. But I guess what I learned in my control systems theory classes that not every time that you can get these kind of signals at all point. And that's where you sort of implement observers, or what we call as estimators as well. And I guess that's also one of your research interests, I suppose, observer theory.
Yeah, so I mean, I would say that is my area of expertise, is observer theory.
Yes.
So, you mentioned estimators or filters, as we also call them.
Yes.
So the difference between observers and filters is really the modeling paradigm.
I see.
Where observers are deterministic system models. Estimators and filters are stochastic system models, but the underlying philosophy for both of them is the same. So, I mean, you mentioned state.
Yes,
right?
yes.
So, another concept that was originally developed in the world of cybernetics and then, made mathematical in my field, systems and control, by a guy called Rudolf Kalman. So the way we think about the dynamics, coming back to that word, of a system, is it's not only about the behavior that happens in time, right? But it's actually the reasons for the behavior. So the example that I tend to use for this, that sort of shows a little bit what the tricky part of it is. If you're in your car and you're driving on a road, right? So there's a curve coming up.
Okay.
So what are you going to do, right? So depending on how reckless you are, you will somehow maybe use the brakes a little bit at least, and you're going to turn your steering wheel.
Yes,
right. And so, these are processes over time, right? So you're going to adjust the steering wheel a couple of times while you're in the curve, adjusting to what's ahead of you. You might reduce the speed a little bit when you get scared and that sort of thing, right? So now you do the exact same thing that you just did in that curve again the next day. But the difference is that yesterday you were approaching the curve at 60 kilometers an hour, and today you haven't paid attention and you're at 80 kilometers an hour. What do you think will happen if you do exactly the same thing as you did yesterday? You'll probably struggle to make the curve, right? Unless you are a very defensive driver. And so this is what dynamics is all about, right? So what is the difference here? The difference is the state of the car at the time when you're entering that bend, right? So that is the only difference. And so, if you think in terms of physics or, the way we think about these kinds of technical systems, today your car had way more energy than yesterday. And so that energy gets converted, for example, into heat, friction of your tires on the road. If you exceed certain thresholds, that becomes catastrophic. Right? And you're going to fall out of the curve, right? And so it's not because you did something different. It's because the state of your car was different. And so dynamics is always about this interplay between how do you interact with the system and what is the stored internal state of the system when you are interacting. So that's sort of fundamentally the thing. And so that already tells you that in order to achieve a control goal, so, things like, well, I want the right temperature on my skin in my shower, right? You actually need to understand the system state. Okay. So in this case, you need to understand, well, what's the thermal energy inside the water tank, right? What is the state of the heating element inside the water tank? At what temperature is it currently at, right? And then, what's the state of the valve that I've turned? Changing the pressure in the pipe and the flow rate in the pipe, right? And so unless I know all of these things, I cannot really achieve that constant temperature that I want to have, because if any of these states is different, then the same action that I take will result in a different outcome. And so now we come to that challenge that you phrased, right? Where sometimes you cannot measure some of these signals.
Yes.
Right? So, in a shower, you theoretically could.
Yes.
Right? So we've got sensors for all of the things that I talked about. There, it's more a matter of cost.
Yeah.
So if you build a shower that has all of these sensors, it's too expensive. No one would buy it, right?
$2,000 shower.
Yeah, exactly. But there are other cases, of technical systems where it's actually physically impossible to make those sorts of measurements. So, an example that always comes to mind is trying to measure the core temperature inside the core of a nuclear reactor. Oh. Well, good luck with that. And so so what observer theory, in the sense that we use it in my discipline, is trying to create algorithms.
Okay.
So an observer for us is a word for a particular type of algorithm that takes measurements of some of the signals that you can measure or have decided to measure of your system, and then uses the model that we've built for the system to try to infer, well, if I've got these measurements and if I've got that model, what must the values of the other signals that I'm not measuring be? Okay, so that's what it's trying to compute. And then, it is a mathematical theory, so you ask the usual questions of, can it be done? When can it be done? If it can be done, do we know how to do it?
Oh, that's important, yes.
And so on.
Absolutely. Well, you did tell us that an observer can be understood as an algorithm. And in my understanding, an algorithm tells us a step-by-step kind of instruction as to how to compute something that we desire, for instance.
Yes.
And in this case, what we can't observe can be computed using that type of algorithm where parameters are taken from what we can observe. Is it correct?
Yeah, so except that we tend to not use the word observe in the way you just did to not get confused.
Oh, right? I see.
So we talk about measured as opposed to observed. Right?
I see.
Right.
And so, we would say that the output of my algorithm, the output of my observer are quantities that I have now observed. Yes, I did indirectly compute them from the things that I could directly measure. But in the way that I think about the system, it's basically as good as if I'd measured it.
Sure. Yeah.
And so keeping in mind that engineers deal in approximate truth. Right? So I know it's not the full truth, but it doesn't matter as long as it's good enough for what I'm trying to do.
So it sounds like the algorithm is a kind of a mathematical way of predicting or maybe explaining the relationship between parameters that we can measure and those that we can't measure.
Yes.
Right. Okay.
So systems and control theory is a very mathematical discipline. It is, it sits squarely between mathematics, engineering, and computing. Right? And so it's, but it is a mathematical discipline at its core. And so which means that it comes with very precise language for these kinds of things. Right?
Sure, yeah.
And so we actually draw a distinction between what we call a predictor and what we call an observer. And so the distinction is that an observer is about giving me the current value, as in right
Makes
now.
Sense. Yeah.
Whereas a predictor is about trying to give me a future value.
That's right.
And so, Rebecca knows way more about this than I do. PID controllers.
Well, I think everybody in control systems and control would know PID.
Yeah, you know that better than I do. And so, one of the things that we had to realize as a field in the 1950s is that sometimes you need to predict a little bit further into the future in order to be able to control now. Effectively.
I see.
Right?
Yeah.
And so, but as I said, it's a mathematical discipline. And so we tend to be very precise with how we call these things.
Right.
Yeah.
It's interesting because I've always been, well, I am more familiar with the way of, say, learning from the past to get the current state right or get some future states right. But it's interesting to know that there are ways where we get some information about future states, like prediction, to get the current state understood right. Yeah.
Well, Song-Yeon, I remember you kept telling me about something which is very similar with that observer thing. That second order cybernetics.
Oh, yeah, absolutely. So, yeah, it came to my mind that second order cybernetics can be quite aligned with what you just told us when it comes to observer theory. Because in second order cybernetics, an observer should be counted and considered in order to understand the dynamics of a system that the observer is observing, along with the environment. So, yeah, I thought that it can be understood at probably at the same level or upper level. There might be a little bit of difference.
Yes, so there is a philosophical difference. And so, from the perspective of second order cybernetics, I think the observer theory that I do would be regarded as first order.
Oh,
okay.
Oh, yeah.
So, one of the differences here is, and I know that some second order cybernetics people prefer the term participant as opposed to observer, right? To indicate the fact that the observer is actually part of the system in some sense, and so influences the behavior of the system through their observation. So this is where we again, as a mathematical discipline, draw very, very fine distinctions. Okay, so the observers that I just described, they work within a modeling and scientific paradigm that is classical. So in the sense that you're building a mechanism that is conceptualized as actually not influencing the behavior of the system. Right? So if I put a sensor somewhere, then I'm trying to construct that sensor in a way that it is actually not changing the behavior of what we call the plant, right? So the system that we are trying to control. So again, Rebecca knows more about this than I do. We know from quantum mechanics that that's not always possible.
Yes.
Right?
Yes.
And so I guess, you could take that as a natural science justification of the second order cybernetics approach if you wanted to, right? That you have to actually account for situations where that you cannot decouple this. It's again worth remembering that as engineers, we deal in approximate truth. Approximately, you always can.
Yeah.
Right? And so, in some circumstances, that's even a mathematical theorem I can prove to you. It is one of the contributions I've made to my field, right? And so the way we go about modeling in this context, again, is that we think of the observer part as the part that doesn't actually influence the system dynamics.
Okay.
It is then the subsequent controller part, as we call it, that does the influencing of the system. So that is how we think, right? And so we end up with a 3-part feedback loop where you've got your system, you take measurements through your sensors, those sensors go into an observer or filter algorithm that produces estimates of the other variables in the system, the other signals that you haven't measured. And then based on all of this information, the measurements and the estimated signals, the controller then tries to influence the system through what we call actuators. Right? So in this case, increasing the current through the heating element. In a fancy shower, you'd have an electronic valve that you can open or close and things like that.
Excellent.
Yeah, excellent. Yeah. Well, it's really so interesting actually to hear different different perspectives rooted from different disciplinary backgrounds, as in how we look at the same problem but from different points of view, like from a mathematician point of view, engineer, or say just a general scientist, or maybe a philosopher as well.
Yeah,
which is pretty interesting. And now we actually can view like a control problem as a cybernetic problem, and even as a philosophical problem.
Yeah, exactly. So, now I finally understand my co-host behaviors when it comes to approaching a problem. So, for instance...
Happy to help.
Well, thank you, Jochen.
Well, I can give you an example. So when we are both hungry, I would always ask Rebecca, okay, so what do you feel like? And her answer would always be like, anything?
Anything.
And so I'd be like, okay, well, we had Thai yesterday and Indian the other day. So why don't we now consider something else? So you see, I guess this is exactly how different engineers are from mathematicians.
Well, I guess we're going to have Chinese then today.
I've just returned from Singapore, so I can recommend that.
Problem solved?
Yes, problem solved. Awesome.
Yeah, thanks a lot again, Jochen, for such an insightful chat.
It's my pleasure.
Well, thanks.